Hello everyone. My name is Gudozhnic Olexandr. I work at EPFL. So there are two labs that participate in the consortium in the TERRINet. So the biorobotics laboratory, the biorobotics laboratory headed by Auke Ispert, which does quite various topics in robotics: amphibious robotics, quadruped robotics, neuromechanical simulations, some humanoids, although that is being kind of abandoned, rehabilitation technologies lately. And another one is the Laboratory of Intelligent Systems, led by Professor Dario Floriano. We do quite some drones, aerial robotics, wearable robotics with haptic feedback, and soft robotics, tensegrity structures, for example. So I'll start by the BioRob platforms. We have this nice testing pool facility indoors. It's it's quite small. It's 2 by 7 meters area, 30 centimeters deep. It was mainly purposed to test the amphibious robots, as you see there, the salamander-like one and the lamprey-like robot. Can be also used to test some underwater robots, not very big because it's quite shallow. Unfortunately, too shallow to have a refreshment during the hot summers, but we have a lake for that nearby. So it has a very nice forced flow system. So you have an array of fans here, underwater fans. So we can test stationary constant speed robot tests. It has a top view camera tracking of the robots. No special requirements or skills needed for this platform. It's quite easy to use. It's just probably you'll need to come with your robot for for testing. Okay. So we also provide some quadruped robots. So the first one here is on Chilla, 5 kilos, about that size. It has spring-loaded pantograph legs design and abduction-adduction mechanism for easy turns and more stability. So we had already one transnational access. The team from Poland used this robot. I'll show you some videos later. And another one is a cheetah cub, a much smaller robot, lighter robot, around 1.2 kilos. Same spring-loaded pantograph legs, but without no adduction mechanism. Both are quite outdated, but still usable. They use x86 computer on board and only programmed in C++. So you need to have some knowledge in C++, and of course in the kinematics of the four-legged robots for using them. Okay. So coming to LIS platforms, so we have this nice Birdly virtual reality flight simulator. It's a 3 degrees of freedom platform that you can use to give people immersive flight experience. It's a bird-like flight experience where you control the flight using two wing-like platforms where you can orient the pitch angle and do a flapping motion. There is also a wind simulator, and there are quite some experience, like virtual experience, provided by the manufacturer. Like you can fly over New York or something similar. So that was used for some studies of influence of VR environments on people. Another platform is the EB fixed wing drone. It's mainly used for mapping and inspection. So it's equipped with a camera and can be programmed to follow a special path to do a mapping, and is combined with a 3D stitching software that we can use to stitch images afterwards. Okay, and the last one is the RoboGen. The RoboGen is the framework. It's actually hardware, open hardware, and software simulator to implement evolutionary robotics. So this pretty simple 3D printed blocks that we can join together using simple servos and a simple microcontroller that well, we use it for teaching students about the evolutionary robotics, but can be used also by anyone. It's a very simple platform. Also, only C knowledge is necessary to use it. In case of these two, no prerequisites. It's basically for everyone. We of course provide some initial training, very basic training about this. And coming to our another nice facility is the motion capture arena. That is a room around 10 by 10 meters, around 5.5 meters high. So it's equipped by 26 OptiTrack cameras. So the position precision is below 1 millimeter. And I also had this slide about how OptiTrack cameras works, but apparently everyone here knows that. I'll come back later if you wish. So that's the usual workflow we use to fly drones in there. So we have usually a drone that's runs PX4 autopilot firmware on Pixhawk autopilot board, and onboard computer we use either Odroid or NVIDIA Jetson TX2, which runs ROS on it, and it has a Mavros node to communicate via Mavlink protocol to autopilot. And this is filmed by the camera, and the positions from the OptiTrack are being sent to the ground station, which also runs ROS and has at least 2 nodes. It's a frame transformation because the frame of the OptiTrack does not correspond to the frame reference of the autopilot, and also the user control node where the user defines the behavior, the high-level behavior of the drone, and that is being connected via Wi-Fi link to the drone. Okay, so we don't provide any drones with the system. So the user should come if user wants to do some experiments with drones. It should bring his own system to to test. But this main workflow is preferable, and we try to ask users to implement this. So I will show you just an example of our in-house built drone that we use for experiments. It's a very simple structure, around 350 millimeters in diameter, less than 1 kilo weight with the batteries, and well, it has Pixhawk 4 autopilot. As a companion computer, there's Odroid on board, and can be optionally equipped with NVIDIA Jetson TX2 and the cameras all around to have some vision experience. And yeah, that's basically it. So we built this in-house because it's very easily repairable in this case, and very modular. If you want to add some additional equipment, it's very easy to do. Okay, I'll show you hopefully an example of a video. So the 3 drones, like I showed previously, are being controlled off-board, meaning that the trajectories are pre-programmed from the ground station, and they're not being controlled manually. It's probably taking too much time. So the idea is to run the drone swarms in this room to do swarming experiments, and eventually equip all of them with the cameras and do other drones recognition and fly them autonomously without using the mockup. But for testing, of course, we use the mockup. So as you see here, all the drones are following the circular trajectories around the room using the code workflow that I showed before. Okay, another example is with the Crazy Fly, small Crazy Fly drones. It's not running. Sorry. So they are pretty simple. They don't have an onboard computer, and everything is run on the ground station. Just the low-level commands are sent to the phones. Okay, so this is of course all with mockup data integrated. So we don't have a real swarming yet. Okay, and I will show you some transnational access experience that we had. So it's not always used to use the drone dome. Sometimes drone got stuck on the net, and it's quite difficult to take them out. Another guy from Poland used the ground robots because his tracking system was not performant enough to close the position loop. So he came for us to test some swarming algorithms for ground robots. And this is hopefully to run also. So this is the on-chiller robot moving. It's another team from Poland that came to test the algorithms of terrain detection by neural network by just measuring the pressure on the pressure sensors on the feet. So see, it's quite maneuverable thanks to the adduction mechanism. I'll just show you another one outdoors. So it's quite robust, but sometimes it fails in the...
Okay.
Unfortunately. Okay, well, thank you for your attention. If you have any questions, I will gladly answer. Thank you. Thank you. Yes?
Can you please send to me or Marcela that picture from Polish guy?
Yes, of course. I think she has already this one. I already sent to her. But I also can send the others that I requested after the mail of her. Okay. It's 3 at each arm actually. Yes, this one has adduction mechanism. Okay, thank you.